All right, hello everybody. This is Dr. Tracy Tubes. I'm here for a supplemental video for the Chapter 7 problem of the low impedance grounding calculations. I tried to do it in the actual course lecture itself, but it became a little. There's so many steps. I don't want to rush it in like 5 or 10 minutes on one page. So instead, I'm going to make a supplemental video that will draw out every single step so we all understand what's going on. We're not skipping steps, we're not trying to condense it or anything, okay? Because I think this is very important to understand every individual step without rushing it. Otherwise, you're just not going to know the big picture and what to do, okay? You're probably going to see this in the quiz or the homework today, this week as well. So this will be additional good reference for that, okay? So let's go ahead and get started. I pretty much made a new PDF called a supplemental PDF here. Okay. So this is a Chapter 7 System Grounding Principles supplemental question. I will put this up on the Canvas course along with the link to this video that I'll host on YouTube. Okay. So just to recap, I just finished the Wednesday meeting with everybody, or the class with everybody. The last part we did was low impedance grounding. I started doing it, but I realized I was running out of paper screen real quick. It was very convoluted and jumbled up. Let's just demystify everything and put the brakes on. Let's do step by step, which is what this video is gonna be. Probably gonna be about 10 to 15 minutes to go through everything. Okay, just to let everybody know. Okay, so we have a low impedance grounding system here, right? We have a transformer. We want to put a resistor here to limit the fault current to 400 amps. Okay, this transformer has X1, X2, X0 impedances that are giving in per unit, right? With that per unit, the base being 100 MVA and 13.8 kV on the low voltage side. Okay, so we are going to put we're going to put a fault right here. And then we're going to try to ask ourselves how much current is going to be flowing through the ground circuit. Okay, this is for a one line to ground fault. Okay, now what are the steps? This is a key part. Right? I've seen people, they just go straight for the math and they don't have a plan. And they're just slamming equations everywhere. Okay, so let's go step by step. Because we're dealing with a single line to ground fault, we must draw the sequence networks. So we're going to draw the zero sequence network first, and then we're going to draw all the networks. So actually, I should add, so we're going to draw the sequence network systems. This is a zero, positive, and negative sequence. Okay. And then we're going to combine them all together. We need to calculate what I1 is going to be, I2 and I0, because you're using sequence network to do fault analysis, we need sequence components, I1, I2, and I0, positive, negative, zero sequence currents. Okay. We're going to have to switch this into per unit currents as well, because the transformer starts with per unit impedances. We got to stick with the per unit system. Okay, that's C. D is we're going to calculate the total impedance of the single line ground fault. We're going to combine impedances together to a simplified circuit. Then we're going to calculate the correct resistance R to satisfy the current restrictions of, remember, 400 amps. Okay. And lastly, this resistance will be in per unit because most of our work is in per units. We're going to have to unconvert it back to regular ohms for the final result. Okay, so this is a B, C, D, E, F steps. Okay, now there's a separate page for every step, so we can see the large, big lettering, what's going on. Okay, so let's go ahead and first start with part A. Okay, so I have the actual circuit diagram for every page, so we don't forget what's going on. So we have a fault right here. That's step one. So remember, draw the zero sequence components and positive and negative sequence component all together. Okay. Now, if you remember, positive sequence component, right? This is you're going to write you can have your N1, and then we're going to have a source, and we're going to have a positive sequence X1, and we're going to have F1. Okay. That's your positive sequence network. Your negative sequence network does not have the source anymore, right? That's shorted. So N2, and we're just going to have the JX2 impedance, right? And we're going to go to F2. Okay, so like ideally, there's a fault happening. We're just going to go through the X2 impedance. Zero sequence system is going to be N0, and we're going to have a zero sequence network. Okay. Now, we're going to combine all this together to a one line to ground fault network, single line to ground fault network. Okay. If you go back to your symmetrical components chapter, you will see that the way to do this is you got to put all the positive, negative, and zero sequence components in series. You have an N1, F1. This is your positive sequence network. Then the negative sequence network is in series. That's F2. Okay, let's draw it a little bigger. And then the last one is your zero sequence network, which also is here, N0, F0. Okay. Let me redraw this positive sequence network just to make it a little more symmetrical. Okay. And this is all in series, and we are adding a resistor in the network for the single line to ground fault. So we're going to have to put a resistor here as well. But the rule here is all resistors, all impedances we put in through either like a tree branch impedance or a resistor we add on purpose, we have to multiply by 3 to add it into the network. Okay. So now we have a sequence network, and remember, current is flowing down each one of these. Okay. This is I1, I2, and I0. Okay. And remember, this is all the current just flowing through this loop. It's a single loop current. Okay. So that's what our network impedance looks like. The key thing is remember what the positive, negative, zero sequence networks look like. Look at the combined network overall. Okay. Now we could go one step further, and we could combine. We could start swapping in actual impedances. Okay. So let's swap in that positive sequence network first. So we're gonna have our source, and we're gonna have a JX1 right here. Okay. So that's the end of our positive sequence network. Let's put in a negative sequence network. That's going to be another impedance. This is JX2. So now that's done. So let's put the third one, zero sequence impedance. That's going to be a third one right here, JX0. Now, because we're only going through the transformer, that's the only impedance that's hindering the fault current. We just have to put the transformer impedances, X1, X2, and X0. Okay. If the system was more complicated, this network will be a little more complicated. Okay. Now, don't forget, we have that resistor we want to put in, so we got to keep that here. So it's going to be 3R. Now, because all the current are all in series, they're all going to flow this way, right? And this is I1, I2, I0. They're all equal to the same number because they're all in series. Okay, so this is a key trick right here. Right, and typically we assume 1.0 per unit voltage before a fault. Okay. So this is the key right here to get started is draw your sequence network, because now we know what we're looking at. Okay. Now remember, we want to limit the current. So now we have to start thinking about what can I do to make I1 and I2 and I0 limited. Okay. The one thing I can change is I could change this. That's what I have control over. Everything else I don't have any control over. So I have to choose a resistor large enough to lower the current down to the level that I want, which is 400 amps on the A phase. Okay. So that's step number one, draw your sequence network. Let's go to step number two. We need to calculate what I1, I2, and I0 are, because that's what we're working with in the sequence network. Now, remember, our fault current we said is 400 amps. Okay. Right here. Now, for a single line to ground fault means only one phase is faulted, which is A phase. The A phase is 400 amps. During this fault, B phase fault current is 0 amps. C phase fault current is 0 amps. The only fault current that I want to see on single line to ground fault is limit IA to 400 amps. Okay. Now, to calculate I1, let's start and just go with the matrix, right? If you remember, we have a matrix I0, I1, I2, right? This is equal to 1/3, and we draw a matrix out, IA, IB, IC, right? IA, IA, IB, IB, IC, IC, right? Now there's some alpha operators. I never memorized which one's which. So easiest thing to do is why I use this program is let's go back to symmetrical components. So I'm gonna go back to my symmetrical components chapter right here and look, I have it right here. I0, I1, I2, everything divided by 3. And we have IA and IB and IC and IA alpha, IB, alpha squared. So alpha and alpha squared. So I have alpha and alpha squared right here. And then this reverse right there. Okay. Now, because it's in matrix form, we're going to add all these together to find I0, I1, and I2. Okay. Now, let's go ahead and remember what are 0 amps. This is 0 amps. Cross it out. 0 amps, 0 amps, 0 amps, 0 amps, 0 amps. Okay. So we don't deal with any of these. So the only thing we need to deal with is IA, because that's the only one that's actually something, which is 400 amps. So you see it's 400 amps everywhere. So we can calculate I1, I2, and I0 very easily. I0 equals 1/3 of 400 amps, right? And that's going to be equal to 133.3, right? 400 divided by 3, yep. 133.3 amps. I1 is going to be the same thing, which is equal to 133.3 amps. I2 is equal to the same thing, which equals 133.3 amps. Okay. Now, does that make sense? Well, let's scroll up real quick and look at our network impedances, right? So notice I1, I2, and I0 are all equal, right? Because right here, they're all equal. It will make sense that all three then will be 133.33 amps. So the numbers are working out. I'm feel confident in my calculation so far because they're all the steps are making sense. Okay, so that's step number 2 is calculate I1, I2, and I0. Now you could just literally calculate one of them and you already know the other 2 to cut time off. But I like to give an explanation of why this we can do this shortcut. Okay, so now we have I1, I2, and I0, but notice they're in amps, and our impedance of the transformer right here are in per units. So we have a disjoint. We need to convert the current into per units, which is the next step. So remember, I1 is equal I2, which is equal to I0. This is 133.3 amps. Now I need to convert this into per unit. So I'm just going to convert I1. So I know I1 equals 133.3 amps. I need to divide that by my base current. Okay. Now, in the lecture slide, I just gave you the base current, but I think I'm doing you a disservice by not showing you how to get it, so we all remember. Let's calculate I base. Okay, I base is going to be, you guys might as well memorize this equation, right? Is your MVA divided by square root 3 times KV line to line. In our case, I base is equal to, what does the transformer look like? 100 MVA divided by square root 3 times 13.8 kV. Okay, that is going to be, I have it all written down somewhere, 4,184 amps. Okay, so coming back over here, I'm going to take 133.3 amps divided by 4,184 amps. Okay, I1 is going to be 133.3 divided by 4,184. It's going to be a very small number, 0.0318 per unit. Okay, so basically we got a pretty, this is 3% of the low current. So we want to lower the ground fault to be a little bit, not too much, not too little, just enough that we could detect it. So 400 amps is reasonable. Okay, so that's my I1. It's 0.0318 per unit. Okay, so now remember, I have my sequence network. I have now my sequence current. So then the next step is let's do circuit analysis. All right, so let's go ahead to the next slide. So let's actually remember some numbers. So I'm gonna write right here, I1 equals 0.0318 per unit. It's very important to keep. Okay, so let's bring that over with us. Just put it up here. Remember, we're pulling a fault right there. Okay. Now, calculate the total network impedance of one single line to ground circuit. So if you remember, our circuit originally, oh, I just covered that number up already. Okay. We have a source. We have our JX1, which I'm just going to start writing in numbers, 0.05 per unit, right? That's my X1. My X2 is also J0.05 per unit, okay? And then my zero sequence is J0.04 per unit, okay? So remember, this is positive, negative, zero sequence. Okay, I'm literally writing in impedances. And remember, we're trying to find 3R. So whatever that is, triple that resistance, that's what we're trying to find. Now, what else do we know? We know the current flowing through here is I1. And I know that is equal to, I covered it up just now, 0.0318 per unit. Okay. Lastly, we assume that we got 1.0 per unit voltage because the system was running normal before the fault. Okay. You know, I'm looking at this, I see all numbers except for one variable, R. So it almost feels like I have a solution in front of my face. I just need to start crunching some numbers together and combining the circuit. Well, the easiest thing to do, so now let's combine impedances. Let's make the circuit smaller and easier to look at. All right, so the source has to stay, but look at all my reactances. I could combine this over to something total, right? I'm going to write over here, JX equivalent is going to equal to be JX1 plus JX2 plus JX0, right? And that can be 0.05 plus 0.05 plus 0.04. Don't forget the J. Okay, so that's going to be 5, 5, 10, 14 per units. Okay. JX. Okay. So if I crunch all those reactances together, I'm going to get a total of J0.14 per unit. So I just added them all up together. That's all I did. Okay, on the other side, we have a resistor, 3R. And this is a closed circuit. Remember, we have 1.0 per unit voltage. Okay, let's say V equals, just to signify. And color coding in red, we know I1, which is equal to 0.01. What the heck? What just happened? Give me a sec. Okay, it's graphical glitch probably. 0.0318 per unit. Okay, so you know, I actually crunched this down. This is a very simple circuit. There's an inductor, a resistor, a voltage, and a known current. The only variable here is R. We can solve this, okay? So again, we just wanted to crunch this network together to get something small and easy to use. Okay, so let's go ahead and go to the last step, which is, or second to last step, which is figuring out what's R, right? Now, I'm going to go ahead and copy this diagram here and bring it down to the next page because that's pretty important. Okay, that's kind of like the roadmap for us. Okay. All right, so let's bring this over here just to remember from the previous section. Now let's convert. Oops, let me bring it down a little bit more. Now, Control Z, save me. Okay, now just a little more. Okay, so now let's find R. Oh yeah, I skipped a step. I'm sorry. So let's move this back up. It's gonna be nice. So slow. We'll get there. Okay, so now part E is I want to calculate R. I have a circuit. We can do basic circuit analysis. Now, don't forget, this is phasors. This can be a little more complicated, okay? Because there's a reactance involved. So let's think about circuit analysis. We have a voltage, right? This is equal to 1.0 per unit. Actually, wait, hold on. Let's just write the actual equation out. We have a voltage. We divide by current, and that should equal our Z impedance, right? Ohm's law. That's all I'm doing. Now, let's fill in what we know. I know voltage is 1.0 per unit. Okay. I know my current is 0.0318 per unit. Okay. I know my Z impedance is 3R plus J 0.14 per unit. Okay. Now notice there's a J on the right-hand side. So this is a phasor problem. Now, I said 400 amps. I didn't give a phase angle. So there's going to be phase angle to this current. We don't know what it is, right? We can calculate it once we know the resistance. But whenever you have a fault, the fault current's going to have a phase angle. Most of the time, we don't really care what the phase angle is because the phase angle is not what does damage. It's really the magnitude. So yes, there's a phase angle involved. But honestly, if I just stick to magnitudes and just not worry about this particular phase angle, I could figure a resistor to lower the current to 400 amps. Because I didn't specify what phase angle has to be. It could be any phase angle. Okay. I just want to make sure the overall current is lower than equal to or lower than 400 amps. Okay. So how can we solve this problem? Right, where we have a questionable a phase angle. Well, at the end of the day, all I care about is magnitudes, magnitude only. So as long as I keep track of magnitudes, I'll be fine. So let's just look at magnitudes. Well, I could simplify 1.0 divided by 0.0318. Let's get a calculator out and quantify that. 1 divided by 0.0318. Okay, that is 31.447 per unit. Okay. And now there's a questionable phase angle involved here. This is going to be equal to 3R plus J 0.14 per unit. Now, if I just think about, well, I just want to care about magnitudes, let's just get the magnitude of the real. So we have real plus J imaginary. If I only care about magnitudes, why don't I just take the real squared plus the imaginary squared, right, and square root it? Isn't that just a magnitude only? Let's just do that. Okay, that makes sense. Okay, so let's go ahead and let me try to go down a little bit. Got way too many screens to figure out where my mouse is. Okay, so let's go ahead and just look at magnitudes only. So this is really just 3R squared plus 0.14 squared square root equals 1.447 per unit. Okay. So I could just get rid of the square root by squaring this side and squaring this side, right? And so then we're going to have a 3R squared plus 0.14 squared. Let's put some brackets here. This is equal to 1.447 per unit squared. Okay, they're all per units, right? If I didn't, I should carry it over. So there's a per unit here, per unit here. Okay, we could solve this math problem, right? So let's put the 0.14 on the other side. So we have 1.447 squared minus 0.14 squared is equal to 3R squared, right? And let's square root both sides to get rid of square on the other side. So, man, I'm already running out of room here, right? So let me just duplicate. Let me organize this a little bit better. Okay, so let's move this up a little bit. I'm just trying to make some space. Okay, we want to do this. All right, so let's go ahead and take all this. Again, I'm just going to shift everything up a little bit just to make sure everything fits on one page. There we go. Okay. All right, so again, honestly, I'm just getting bogged down a little bit in mathematics, but that's fine. So we're going to take 1.447 squared minus 0.14 squared, square root both sides to get rid of the square on this side. So we just have 3r. We're pretty much done, right? I mean, at this point, r just equals to 31.447 squared minus 0.14 squared square root divided by 3. Okay, this is just hard numbers. Let's get the calculator out. Okay, actually, I already did it. So, I got 3.1. Yeah, let me just go with the calculator. 31.447 squared minus 0.14 squared power to 0.5 for square root divided by 3. I got 10.48 per unit. I might rounded this just slightly off. I think my notes say 10.45 or whatever. This is close enough. So that's our R. This is literally what we're going for, right? We just had bogged down a little bit of math, but we got out of it. So now we're not technically done because this is per unit. You don't buy resistors per unit. You buy them per ohms. So the very last step, which I'm going to rewrite R equals 10.48 per unit, is how to convert resistance and per unit back to hard ohms, which is what we want. So this is your basic per unit example. So if I know my R is equal to 10.48 per unit, I need to multiply by my Z base to get the correct value. Okay, now, so it's 10.48 per unit times something. We got to figure out what that something is. So let's do a sidetrack Z base. Okay, if you remember, to find the base impedance is always your KV line to line squared divided by your MVA. The K squared and M will cancel out. So your Z base in this case, because the fault is on a low side voltage bus, so we're going to use a low side voltage. This is 13.8 kV squared divided by 100 MVA. Okay, and what is Z base? It's like maybe 2 ohms, be my guess. 13.8 squared divided by 100. I don't know why divided by 100. 1.904 ohms. Okay, that's my Z base. All right, let's plug this back into the original equation. 0.194 ohms. And my total R at the end of the day is just those two numbers multiplied together. So let's do answer times 10.48. I got 19.96 ohms, and that's it. So at the end of the day, this resistor right here is 19.96 ohms. Okay, yeah. And that's the answer. Okay. So that's how you solve this problem. The resistor does throw a big wrench into the problem because you got to compare reactance versus resistance. Okay. You can't do this purely on reactance. And if you do it only through reactance, you don't have to do this square root stuff, right? Because you could just add all the reactances together, right? Because they're all 90 degrees and the math is easier. But 90% of all this work is all going to be the same. You still have to go through A, B, C, D, E, F processes, right? It's just if you just use a reactance, then just right here, instead of using the square roots and all that, just add the reactances together, right? Makes your life easier. There's examples in the book, which I did reference, I think, the very beginning. I should. Is 7.71 to 7.72, right? That's pretty much where it came from. The numbers have changed, obviously. Okay. So that's pretty much it. Let me know if you have any questions. I'm hoping that this guide video will make doing your homework and quiz a lot easier because now we have a step process. Okay. So let me know if you need anything else. I think we'll call it a day and see you guys on the next lecture.